All right, this is homework number 33. The first problem says find dy dx and the slopes of the tangent lines shown on the graph of the polar equation. So I guess I cheated a little bit on this because looking at this picture, like these definitely both look like tangent slopes of 0. I will find dy dx, and so if I was really worried about it, I could confirm by plugging in my angle and getting 0. But to save time, I am only going to actually evaluate dy dx at this angle because I'm not sure what that slope is just by looking at it. Okay, so I am going to say dy dx evaluated at theta equals pi over 2 looks like it's definitely 0. If this were the AP test, I would be, actually plugging in the angle, but okay, whatever. And so does this one. Let me include this in my box too. So dy dx evaluated at theta equals 3 pi over 2. That one also looks like 0. So, okay, so there's that first part. Now, I do need to find dy dx and plug in theta equals pi because I can't just look at that slope and see what it is. So remember that for the formula for slope, we need both r and r prime. So I'm going to write down r prime. So the derivative of 2 is 0. The derivative of 3 sine is 3 cosine theta. Not sure why my pen is being so spotty. And I like to write out the memorized formula for dy dx before I start plugging stuff into it. So it's r prime sine theta plus r cosine theta over r prime cosine theta, this pen is driving me nuts, minus r sine theta. It is in your interest to memorize this because if you don't memorize it, then you have to do dy d theta over dx d theta. And that would be a product rule on top and a product rule on the bottom because y is r cosine theta and and x is r. Y is r sine theta and x is r cosine theta. These two things are the result of doing product rule. So it saves you that step. And then I'm going to throw in what I have. So 3 cosine theta, that's r prime, times sine theta, plus, because r is two terms, I'm going to put this cosine theta out front. I will end up distributing that through. So cosine theta times r, which is 2 plus 3 sine theta. And in the denominator, r prime is 3 cosine theta times another cosine theta. So I'll make that cosine squared theta. Minus, same thing here. I'm going to put the sine out in front and then the r in parentheses. And I'm not going to simplify this too much, but a little bit. I'm just trying to plug a number into it. So I don't need to go crazy with the simplifying. But if I were to distribute this cosine through, I would have 3 cosine sine plus another 3 sine cosine. So that's 6 cosine theta sine theta. Plus there'd be a 2 cosine theta. Nope. And there's not a lot that simplifies down here. 3 cosine squared theta minus 2 sine theta minus 3 sine squared theta. All right, so that is dy dx. So find dy dx. There it is. And then evaluate dy dx at this polar coordinate where the theta, I need theta, that's the input here, right? Where the theta is equal to pi. So 6 times cosine of pi is negative 1. Sine of pi is 0, so that term goes away. Plus 2 times cosine of pi, negative 1. By the way, sorry, I know we did all this in pre-calc, so sometimes I forget that it's been a while since you've done it. Here's pi. Here is pi's coordinate on the unit circle. Cosine is x. Sine is y. All right, so 3 times cosine squared, negative 1 squared will be 1, minus 2 times sine of pi, 0, minus 3 times 0 squared. So all these 0 terms are gone, and we get negative 2 over 3. Negative slope is a good sign. I can see that negative 2/3 seems reasonable, so I'm happy with that answer. And again, if I wasn't sure on these zeros, if I plug in pi over 2, at pi over 2, cosine is 0 and sine is 1. So it looks like you will get 0 if you plug that into this formula here. 0, 0. All right, 64. Again, I'm going to, in interest of time, I'm going to cheat a little bit on these. This looks like a vertical tangent. So dy dx evaluated at theta equals 7 pi over 6. That looks to me to be undefined. And dy dx, if I evaluate it at 3 pi over 2, this looks like a horizontal tangent, so that one's probably 0. And I could plug those two angles in to whatever formula I'm about to get for dy dx to verify if I wanted to. I like to distribute r through, so let's make this 2 minus 2 sine theta. That's my r. I just think that makes r prime easier to find. So r prime would be negative 2 cosine theta. And I'm going to write out my dy dx formula again because right here, I'm not sure. I can see that's a negative slope, but I'm not exactly sure what number it is. So dy dx is r prime sine theta plus r cosine theta. In my brain, to remember this, I think of it as like tangent sine over cosine. I just have it in that order. And then down here, it's just like the opposite of everything. So this is cosine, this is a minus, this is minus r sine theta. All right, and then let's plug in what we have. So negative 2 cosine theta sine theta plus r is 2 terms, so I'm going to put the cosine out first. Cosine times r, which was this, over r prime, negative 2 cosine theta, so cosine squared theta, minus, I'm going to put the sine out here first, and then r, 2 minus 2 sine theta. I could leave it as is and plug stuff in, but I think I'm more likely to make a mistake, so that's why I'm going to distribute a bit. So I have negative 2 cosine sine. There's going to be another minus 2 sine cosine, so that's minus 4 cosine theta sine theta plus 2 cosine theta over, I'm just going to distribute this a bit, negative 2 cosine squared theta minus 2 sine theta plus 2 sine squared theta. Right? So that's dy dx. And then this time, remember this is r theta, so the theta is 0. So we want to evaluate dy dx at theta equals 0. And as I'm doing unit circle trig here, at angle 0, the ordered pair is 1, 0. So cosine is 1, sine is 0. All right, so negative 4 times 1 times 0 plus 2 times 1 over negative 2 times 1 squared minus 2 times 0 plus 2 times 0 squared. Zeros are gone. This is giving me 2 divided by negative 2, so a slope of negative 1. Seems reasonable. It's a negative slope, at least that's a good sign. All right, for the next one, find the points. Now, this does not specify, does it mean XY points or not, but they're points to the polar curve. So I'm going to go polar. It'll be less work for us as well. So when it says find the points, I need to identify the r theta combo of the horizontal and vertical tangency, if any, to the polar curve. So horizontal tangent, dy dx equals 0. Vertical, dy dx is undefined. So let's find dy dx. To do that, I need r and r prime. So r prime is minus cosine theta. And here I go again, writing out my formula because I just can't keep track of it in my head if I just go right to plugging everything in. I probably will make a mistake. So, all right, so here's the formula. Now let's plug stuff into it. So negative cosine theta times sine theta plus, put the cosine here, times r, 1 minus sine theta. I just like doing this because I will distribute. R prime negative cosine times cosine is negative cosine squared theta minus, put the sine out front, times r, 1 minus sine. Now you're going to be setting the top and the bottom equal to 0, so you can work on them separately if you want, or I'm just going to clean it up a bit here. So negative cosine sine minus another cosine sine would be minus 2 cosine theta sine theta plus cosine times 1. That's as far as I'll take the top. Bottom down here, we've got negative cosine squared theta minus sine theta plus sine squared theta. So this is my dy dx formula so far. All right, now there will be a horizontal tangent anywhere dy dx equals 0. Now I say this, but there's one caveat to this. Anywhere the top of this equals 0, but the bottom cannot equal 0. So I'm going to find all of my answers for horizontal tangent and for vertical tangent anywhere dy dx is undefined. But if they have any angles in common, I have to exclude those. So if you, let's just say you plug in pi over 2 and you get 0 over 0, that's one of those indeterminate forms. So we will throw that out. That's not a point of horizontal or vertical tangency. All right, so if dy dx is equal to 0, it means this top part is equal to 0. Negative 2 cosine theta sine theta plus cosine theta equals 0. We need to solve this, so I would factor out either a negative or a positive cosine theta. If I take out the negative GCF, I get positive 2 sine theta minus 1 equals 0. So either way, it's not going to matter. You're getting that cosine theta could equal 0 or sine theta could equal 1/2. Answer these just within 1 unit circle. So cosine theta equals 0 if theta equals pi over 2 or 3 pi over 2. And sine theta equals 1/2 in quadrants 1 and 2, it's positive. And the angles are, reference angle is pi over 6. So pi over 6 and 5 pi over 6. So I'm not going to find the r thetas for these yet because if vertical tangent has any of these answers in common, I'll throw them out. So vertical tangent is if negative cosine squared theta minus sine theta plus sine squared theta equals 0. Now to solve this trig equation, you want to get something you can factor, but I can't factor this right now. Because these two terms are in terms of sine, and I can't do much to get rid of a sine theta, I'm going to trade out minus cosine squared with its Pythagorean identity, which is 1 minus sine squared theta, minus sine theta plus sine squared theta. They will expect you to be able to work with the basic trig identities that we had in pre-calc, which were the Pythagorean and maybe a little bit of our like reciprocal identities and quotient identities and stuff. So distribute this through. This is going to make plus sine squared plus another sine squared. So that's 2 sine squared minus sine minus 1 equals 0. This is a trinomial I can factor. The only way to break up 2 sine squared theta is 2 sine theta and sine theta. The only way to multiply to 1 is 1 and 1. I've got to make it plus and minus so that I get minus 2 theta plus, or minus 2 sine plus sine. We'll make it minus sine in the middle. This means that sine theta could equal negative 1/2 or sine theta could equal 1. And the reference angle here is pi over 6, but now we're in quadrants 3 and 4. So 7 pi over 6 and 11 pi over 6. So nothing in common with the horizontal tangent. Sine theta is equal to 1 only at the top of the circle, pi over 2. So now it's pi over 2 that they have in common, so we have to throw that out. But every other point is different. So now we need to find the r theta for all of those. All right, so at 3 pi over 2, find r of 3 pi over 2. Plug that back into your r equation here. 1 minus negative 1 is equal to 2. So there's a horizontal tangent at the polar coordinate 2, 3 pi over 2. And then find r of pi over 6, which is going to be the same as r of 5 pi over 6 because the r equation has sine in it, and sine of pi over 6 and 5 pi over 6 we just said was positive 1/2 either way. So 1 minus 1/2 is 1/2. So 1/2 pi over 6 and 1/2 5 pi over 6. Those are different points. You're facing different angles and going forward. So even though sine of pi over 6, 5 pi over 6, even though it gives you the same value, those are two different locations. All right, same idea here. We need to find r of 7 pi over 6, which will be the same r as 11 pi over 6. 1 minus sine of both of those is negative 1/2. So 1 plus 1/2 is 3/2. So r is 3/2, and we have 7 pi over 6. We also have 3/2 and 11 pi over 6. All right. Sketch a graph of the polar equation and find the tangents at the pole. So you don't need polar graph paper for this. Just make a little chart. 5 sine theta. Give yourself just a little x and y axis. So when we put in 0, we get 5 times sine of 0, which is 0. So the first point is 0, 0. Plug in like maybe pi over 6 because that makes sine equal to 1/2, 2.5. So just estimate. Pi over 6 is about here. Call that pi over 6. And then you're going forward 2.5. Right, and then I'm going to skip over pi over 4, pi over 3 because those give me radicals. So I'm going to hop up to pi over 2. That's 5 times 1 is 5. Face pi over 2 and go forward 5. And then maybe 5 pi over 6 in quadrant 2, which is 5 times 1/2. So face 5 pi over 6, go out 2.5 units. And then if you put in pi, you get back to 0. So this is supposed to look like a circle. My sketch is going to be a bit rough, but yeah, if you have 5 sine or 5 cosine or whatever number, if it's just r equals sine or cosine, it'll be a circle if there's nothing else added or nothing in front of the theta. Find the tangent at the pole. So the pole is the origin, 0, 0. It looks a lot like 0 to me. I will confirm by finding a quick dy dx. So dy dx is r prime times sine theta plus r times cosine theta over r prime times cosine theta minus r times sine theta. Now remember, we're at the poles, so we're evaluating dy dx before I plug anything in. At theta equals, let's just say 0 is the first place that I put that in. And remember, that means that r equals 0 right there. So actually these two terms can kind of go away. And then if it's just r prime over r prime, it's just really just sine over cosine of theta. So it's really just tangent of theta. And what's the slope at 0? Dy dx would equal 0. Tangent of 0 is equal to 0. So I can confirm that mathematically. I think I did more work. I didn't cancel these out on my key that I posted. But yeah, if you plug in everything for r and r prime, you're still going to get 0 in the end. Okay, and then this true or false section. So these are all true. Disclaimer right ahead. So if r1, theta 1, and r2, theta 2 represent the same points, then r1 in a polar coordinate system, then r1 has to equal r2 in absolute value. So this is true, and it's because we know that they do represent the same point. So the only way for that to happen is like, I'm just going to go with like, say it's like 2 pi over 2. The same point would have to be like, maybe I face 3 pi over 2 and go backwards. But the r can't be anything other than 2 or negative 2. Otherwise, you're not going to land in the same place. You will have not walked far enough, or you will have walked too far. So that's true that the absolute value of 2 would have to equal the absolute value of -2. You can't have 2 and 3 or something like that. Okay, next one. R theta 1 and R theta 2. So notice they don't have R1 and R2. That tells me this is the same R. They represent the same points on the polar coordinate system as long as theta 1 is equal to theta 2 plus 2 pi n for some integer n. This is true because if R is the same, so say you have 2, let's just do our 2 pi over 2 again. What's another way to get to that same point? Face a coterminal angle to pi over 2. So I could add 2 pi to that. If I say face 5 pi over 2, you're still facing pi over 2, same location, and you're going forward. So yeah, this is true because you could add, that was me adding 2 pi. You could add or subtract any number of 2 pi. And we used to say 2 pi k, kes, in pre-calc. But yeah, that would get you to any other polar coordinate. Polar coordinates are infinite. You have infinitely many possibilities. These are all true. So why is number 121 true? So if x is greater than 0, so on the x-axis, you are only on this side, then the point xy in the rectangular coordinate system can be represented by r theta, where r is square root of x squared plus y squared. That's our formula for that. Theta is arctan y over x. So this is true because when you do arctan of anything, whether it's positive or negative, if you do a positive number, you get a quadrant 1 angle. If you do arctan of a negative number, it gives you a quadrant 4 angle. It'll say negative pi over 6 or negative pi over 4 or whatever. And so, yeah, so your theta would only be a quadrant 1 or a quadrant 4 angle, and you would be walking forward r units. And those x values are all positive. So yes, doing arctan and using Pythagorean theorem for r, they will give you only quadrant 1 or quadrant 4 solutions. Last one, the polar equations for this and this and this all have the same graph. So I can answer this one without graphing. We have an identity, they're called the even and odd identities, where if you have a negative inside of a sine function, that's the same as negative sine of that angle. And that's because sine is an odd function. So we were using function behavior. F of negative x for an odd function is negative f of x. So these two are definitely the same. The question is, do you get the same, this is a rose curve, do you get the same rose curve from this as you do if it has a negative out in front? I believe the answer will be yes. It's just if you were to generate them, you would start on different petals. But let's just check r sine 2 theta. So if we put in 0, we get 0. If we put in pi over 4, we're going to get sine of 2 pi over 4, which is 1. So there's the edge of that petal. So the first petal would be like in quadrant 1. And then let's just go to, and this is going to have 4 petals and they'll all generate out. Let's look at if it's negative sine theta. If you put in 0, you get 0. If you put in pi over 4, you get negative sine of pi over 2. That's negative 1. It's back there. So yeah, you'll get this petal to start, but they're both going to have 4 petals. And because petals are symmetric, if this is the first one I did, there's going to be one over here and here and here. So yes, this is true as well. All right, that finishes this video. Come in and see me if you need help with any of this polar dy dx stuff.